Have you ever read a headline claiming scientists make a significant discovery and wondered what that actually means? Let's talk about statistical significance because it doesn't actually mean important or true. Statistical significance is how researchers differentiate between what happens randomly and what happens because of an intervention. It's the backbone of good research, and it helps scientists to determine if their results are genuinely meaningful or they're just random. If you think about your music streaming service's shuffle feature, like Spotify's shuffle feature, and imagine you suspect it's not truly random because every second song is a Britney song, but you only have one Britney album on that device. Statistical significance would tell you this pattern is probably not just random luck. Something else is happening here. We can use another real-world example. Say I'm testing a new vaccine against a virus, and I give 1,000 people the vaccine and 1,000 people a saline solution. That's just salty water, it's a placebo. And then I track who gets sick. Before analysing any data, I need to figure out what I'm testing with something called the null hypothesis. That's the nothing special happening here explanation. For our vaccine, that would be this vaccine has absolutely no effect, and any differences we see between the two groups are just random chance. The alternative hypothesis, that's what we're trying to prove, it's what we're actually testing, and that is this vaccine actually works. So I need to decide how certain I want to be before claiming my vaccine works and how much randomness I'm willing to accept. Basically, is it luck or is it legit? We need a threshold, and it's better to define this threshold before you do the test itself. Typically, scientists use a threshold of 5%, which they call p-values of 0.05. It basically means that if we repeated the experiment 100 times, we would expect this difference, meaning the difference between the two groups, is found 95 times out of 100. It's reflecting a genuine underlying pattern, not just a coincidence. With things like clinical trials and vaccines, the threshold becomes much smaller, as you would expect, because the stakes are really high, so you're much less willing to accept a lot of randomness. Maybe only accepting results when these differences are found 999 times out of 1,000. In my example, after 6 months, 80 people in the placebo group got sick, but only 40 people in the vaccine group did. That's a 50% reduction. My statistical analysis gives me a p-value of 0.001%, which is way below our threshold. So we would call this result statistically significant, and we would reject the null hypothesis. So we could confidently say that this vaccine works. But here's where things get tricky. Statistical significance doesn't tell you how much something works, just that it probably has a relationship. Statistical significance also doesn't tell you if something matters in practice. Imagine skincare. And a skincare company is testing a new anti-aging cream, and their clinical trial shows that the cream significantly reduces wrinkles. Sounds amazing. But when you read the fine print, this significant reduction means wrinkles are decreased by 0.02 millimeters on average, something that the human eye could never detect. So the result is statistically significant in the lab, but practically meaningless. You won't see any reduction in wrinkles in the real world. So remember that 5% threshold. It's kind of arbitrary. It's just a scientific tradition. There's nothing magical about 5%. It's just how we decide if something is strange enough for it to be unlikely to happen randomly. For high-stakes decisions, scientists might use 1% instead. For preliminary research, they might use 10%. It depends on the context of the research. And this matters when you see headlines like, "This study has found a significant link between X and Y," and the media often drops the statistically part and just says significant. And that makes you think that the effect is large or important when it might be tiny or not actually make a difference in the real world. We also need to think about other conditions. For example, if you were to collect data in Australia on ice cream consumption and shark attacks, you would probably find a statistically significant result. This might lead you to interpret that eating ice cream causes shark attacks. But this is why it's so important to dig into the research itself and understand the data behind the article. No, eating ice cream doesn't cause shark attacks. It's just that when the weather is nice, people eat ice cream and also swim in the sea more, so people get attacked by sharks more. So next time you hear about a statistically significant finding, you need to ask yourself a few questions. How big is the actual effect? Not just, does this effect exist? Was the study large enough for it to be reliable? Did they test 1,000 people or did they test this on 2 people? And does this difference matter in real life? So hopefully you understand a little bit more about what scientists mean when they say statistically significant, but also that the question behind the research and the study population is really important too.